This is the Radio Shack Micronta Digital Logic Probe 22303. First advertised in the 1987 Radio Shack catalog, it was sold for $16.95. A logic probe is an inexpensive handheld test tube used for analyzing and troubleshooting digital circuits. It indicates the state of a digital circuit, which can either be 0 or 1. If the probe indicates a 0 reading, the circuit is in an off or no voltage condition. If the probe indicates a 1 reading, the circuit is in the on or voltage condition. The probe is usually powered by the circuit being tested, which is why there are 36-inch red and black alligator clip leads attached to the rear of the probe. This probe is compatible with both TTL, which is transistor logic, and CMOS. The pulse detecting electronics typically include stretcher circuit, ensuring even very short pulses are visible on a LED. Now that we've covered the basics of this tool, let's move to School Tube and discuss how to use it. We will review 3 basic gates and their truth tables, then use the voice chip to demonstrate how to use the probe. Please note, I haven't taught or used this technology since 2009, so my understanding may be a bit rusty. Now we're talking about the most basic gates of all gates. NOT gate or an inverter gate. So, you put a volt on here, or you put a high here, which is the 1. Put a 1 here. The output out here, because this is an inverter, this is a NOT gate, it's going to be 0 here. So this is a 0. So now get rid of that, and now let's say that you get rid of that. You turn that to 0. If you put a 0 here, get rid of that, this becomes 1. And that is how that works. Now we're looking at a NOR gate. A NOR gate has an inverter on the output. So how does this work? We already established if we put a 1 and a 1 here, we're going to get a 1 out. But this is inverted. So a 1 and a 1, 1 plus 1 on a NOR gate equals 0. Now you put a 0 and a 1 on an OR gate, you get 1, but this is an OR gate. So 0. You flip them, it's going to be a 0. You put 0 and 0 here, 0 volt here, 0 volt here, you're going to get a volt out here. You're going to get a 1 state out here. And that inverter converts what's coming out of the OR gate into a NOR gate. Another word for inverter is N-O-T. Not. So these mean the same thing. Okay. This is a AND gate. So, AND gate, 2 states. So let's drop the states in here. 1 and 1, 0, 1, 1, 0, 0, 0. Okay. I just showed you how OR gate equals 1. So your state out here is 1. So 1 and 1, 1 and 1 equals 1. Let's go to the bottom state. 0, 0, 0. 0 and 0 on an OR gate, on an AND gate, 0. So you drop these and change these to 1 and 0. So now with that you have 1 and 0. Remember, this is an AND gate, not an OR gate. Come up with a 0. So you flip those and turn that to a 0, and you turn this into a 1. That's going to be a 0. So that said, now let's turn this into a NAND gate. So now you have an inverter out here. So you have 1 and 1 and 1. 1 plus 1 equals 1. But it hits in that inverter. Remember, I told you an inverter is a inverter equals NOT, or not. So it inverts. So 1 plus 1 equals 1, except when it's inverted, which means it equals 0. So if you get 0 plus 1, 0 plus 1 on an AND gate, AND gate, equals 0. But this is a NAND gate, so that's a 1. Flip those two signals, or signatures, or whatever you want to call them, which is 1, 0 equals 0 in an AND gate, but we're talking about a NAND gate, so that would be 1. If you flip both of these and turn both of those into zeros, 0 plus 0 equals 0, except when it's a NAND gate, that's going to be a 1. So that's how that works. This reverses. This right here reverse whatever this output is that's coming out this AND gate, it reverses it. Okay, looking at this, this is our speech synthesizer from the last video. Okay, if you go through this, you can't see it, but right here there's a circle here that says, that indicates that this is pin 1. Okay, then you will go through this 1 through 14, 1 through 14. And then it starts at 15 all the way up to 28. And that's what this little pin configuration tells you right here. I don't know if you can see it, but there's a little circle here. That circle corresponds to that circle right there. So what I would do if I was using this to see if this is actually working, I would go to pin 28, which is this last pin, because, and I say that because that's some kind of oscillator. As it says right here, it's an oscillator, which means it's some kind of, it's a multivibrator of some type. So this is going to be on, off, on, off, on, off type stuff. So these two pins, as it says, oscillator 1, oscillator 2, so some kind of multivibrator, Also, I'm looking at pin 26. It says some kind of ROM clock. So whenever you deal with a clock, you're dealing with basically a 555 chip. I think it's 4 pins on this thing. Basically a 555 chip. Like your microwave has a clock in it. If it's a digital microwave, it has a clock in it. And I don't mean a clock that's in 1 through 12. It has this chip inside, some variation of this 555 chip. This is a timing chip. Basically, they have 555, 556, and several other chips. But whenever I built something, I usually use the 555 and 556 chips. There's more chips in this family, but these are the 2 basic chips from the 80s that everybody used. That tells me that there's a clock of some kind in this chip. Because there's a clock in there, I can take this probe, and this probe is going to tell me if there's a pulse, if this pin here is locked in high, or if this pin is locked in low. That's if this is a TTL. And that is what you're doing. You're checking that with this probe to see if your signal that's supposed to be coming out is actually coming out. So now, I just told you those chips that I will be looking at. It said 28, but I'm looking at this one. 28 is right here. Here's your clock right here. Some kind of clock circuit here, and you got some kind of megahertz crystal here. So pin 28, I can go to pin 28, which is the last pin. 27 and 28 is going through some kind of clock system, and so that determines, I guess, the rate of speed that the voice is going to talk to based on what this frequency is. It's 3.12 megahertz coming out. So with these, I can check it with there. I also have some pin 24 says digital out based on the schematic. So I will come here and see what kind of state I have here, because this is going to be giving signal, some kind of signal out. It's digital. So, and from here, it's going to move to out of that chip to this op amp, operational amplifier. This is an audio. This is your audio, because there's your speaker right there. So this, I'm going to somewhere on here on the screen, I'm going to superimpose the basic design for this, so you can see what I'm saying. But yeah, this is another. It could be a chip. It can look like a capacitor with 5 or 6 leads on it, or something like that. It can look. It has various configurations. That's what I'm trying to say. And so this comes out of this chip. The signal comes out of this chip, comes down, hits this op amp, and then it comes out to a speaker. And that's how that works. And that's what this does. This probe, the whole point of this probe is to make sure your clock circuit inside this chip is giving you what you're supposed to have. That's what this probe does. It tells you that this chip is not burnt out, bad, or whatever you want to say, or let's reverse that. The chip is still good. And so that's what this probe does. The probe was invented by Gary Gordon in 1968 while he was employed at Hewlett-Packard, or as we call it today, HP. There you have it, the Radio Shack Micronta Digital Logic Probe 22303. If you like this video, please like, share, and subscribe. Thanks, and have a great day.